Hello and welcome to this seminar on energy codes and standards from the Steel Framing Industry Association. This is one of a series of educational programs related to the use of cold-formed steel in building construction. You can find the others at cfsteel.org. This seminar will help us gain an initial understanding of today's major energy codes and standards in light of dramatic changes that have occurred over the past several years. We'll address why energy codes are important and how they overlap with and impact the structural system now more than ever. We have several primary objectives for today. First, we'll discuss how the overlap between various systems in a building has become increasingly important over the past decade. This is particularly true of the way insulation requirements impact framing systems. Second, we'll provide an overview of the two major codes and standards used in the United States, the International Energy Conservation Code, or IECC, and ASHRAE Standard 90.1. Third, we'll address how the major codes and standards are structured in terms of prescriptive compliance paths and demonstrate their application. Fourth and finally, we'll briefly touch on potential ways to optimize the building design through performance compliance paths. Note that this is an overview and not a design seminar. Although the IECC and ASHRAE 90.1 are the two most widely used energy standards, some jurisdictions opt to adopt them as is, while others adopt them and make some local amendments. A few jurisdictions, such as California, develop their own separate codes that aren't addressed in this seminar. However, even though specific insulation levels or other requirements may differ, most of the codes in use today have similar compliance options to those presented in this seminar. You might not have been impacted by energy codes in the past. Except in a few jurisdictions, they really haven't been taken seriously until more recently. Although many jurisdictions have adopted an energy code for decades, enforcement wasn't necessarily a priority. That started to change in the 1990s, but at a relatively slow pace. The 2010 American Recovery and Reinvestment Act, often called the stimulus package, quickened the pace by placing some strings on states that accepted stimulus funds from the federal government. One of those strings is that states had to adopt the 2009 IECC and subsequent later editions on a specific timetable. The act also required 90% compliance to be verified by states. Because ASHRAE 90.1 is referenced in the IECC, it was also swept into the legislation. In addition to the increased adoption and enforcement, a few other reasons began to impact why energy codes affect cold-formed steel construction. Probably the most significant issue is the impact of continuous insulation, which is now required in almost all buildings. Continuous insulation is typically installed on the exterior of stud walls in the form of a foam board similar to that shown in pink in this picture. It was non-existent in early energy codes for framed construction, but became a standard requirement as the focus of energy requirements turned towards reducing the thermal bridges across framing members. We've also seen requirements for windows, doors, and other components start to tighten. Although this doesn't directly impact the framing, indirectly, it reduces the flexibility of designing the envelope with cold-formed steel under the performance compliance options. We'll talk more about that later. Pressure to tighten up energy codes was always present, but the introduction of green programs such as LEED also increased this pressure, as regular codes didn't want to fall far behind their green counterparts. Probably the highest impact issue with regard to cold-formed steel framing is the addition of continuous or foam insulation on CFS walls. Although there are simple ways to comply with the requirements without continuous foam on roofs and crawl spaces, it is much more difficult with walls. Beside higher costs, some of the other issues related to continuous insulation on walls include cladding attachments, thicker walls, sheathing and bracing attachments, and detailing issues at openings that need to be addressed. There are also some fire propagation requirements that are part of the IBC and most major building codes that are introduced with foam insulation. Even though ASHRAE 90.1 and the IECC are adopted widely in the United States, the specific edition varies from jurisdiction to jurisdiction. Throughout this presentation, we'll be talking about the 2018 IECC and the 2016 edition of ASHRAE 90.1. To understand the issues that impact cold-formed steel, or CFS, we need to understand the scope of the two major energy code documents. The IECC covers residential buildings, such as single-family homes and townhouses under 4 stories, as well as commercial and other larger buildings. Residential buildings such as hotels or larger multifamily structures are considered commercial buildings under the IECC. Chapter 5 is our focus today because of its focus on commercial and mid-rise construction that makes up the bulk of the steel framing market. The IECC also incorporates ASHRAE 90.1 by reference as a compliance option. The 90.1 standard is important because it is often referenced in specifications for government construction projects. ASHRAE 90.1, on the other hand, defines their scope by what it doesn't include. The title is pretty self-explanatory. It covers all buildings except basically smaller residential structures. In addition to building types, there are some further scope issues that are important. For example, the scope of both the IECC and 90.1 is not limited to new construction, but includes alterations, repairs, and similar projects. So, for example, a tenant build-out would be included. The IECC and 90.1 each exempt buildings that do not use any energy. The IECC further exempts some buildings that are termed low-energy users, as well as greenhouses. The systems covered in the IECC and 90.1 are not limited to the thermal envelope. Both are similar in that they have a series of upfront sections covering the purpose, scope, and issues like enforcement. From there, they both include a prescriptive set of thermal envelope requirements, as well as prescriptive requirements for other systems, as shown here. Both documents also have at least one performance path where these other systems come into play from a whole building compliance perspective. There are some basic yet important terms that describe the thermal performance of insulation versus an entire assembly. Both the term R-value and U-factor will come up throughout the presentation today. The R-value describes the ability of insulation or a material to resist heat flow. A higher R-value is better than a lower one. The U-factor is another way to describe thermal performance. For example, a wall U-factor describes the total performance of the wall, including the impact of studs, sheathing, insulation, and gypsum board. Conversely, an R-value typically just defines the performance of the insulation or a specific product, such as sheathing. A lower U-factor is better than a higher U-factor, as opposed to the opposite for the R-value. There are two different types of compliance paths in both documents, prescriptive and performance. The prescriptive paths offer simple tables with insulation values and other requirements for each component of the building. The performance path relies on simulation software. The prescriptive path has 3 different options: the R-value approach, the U-factor approach, and the UA alternative or UA trade-off approach. The UA trade-off approach is called by different names in the IECC and 90.1 documents, as shown in the slide. The R-value prescriptive approach has always been the way to go in the past, but it may no longer be the optimal path due to continuous insulation requirements. There are multiple performance paths in the ASHRAE and IECC documents. In general, the R-value compliance process is the same in each code. First, the IECC and ASHRAE 90.1 both contain climate zone designations for all locations around the United States. ASHRAE also covers other countries. A simple climate zone map is provided in both documents. This specific map is from the 2018 IECC and was developed by the United States Department of Energy. It does matter which document you are required to comply with, because the 2016 ASHRAE 90.1 map differs slightly from the 2018 IECC. Tabular lists are also provided to make it easier to pinpoint a location's climate zone. Once the climate zone is determined, the next step is to look up the appropriate R-value requirements in each document. The R-values are minimums, so they must be met or exceeded. As an example, we'll look at determining R-values on a 5-story hotel in Richmond, Virginia. With the R-value prescriptive approach, we first will reference the climate zone map in Chapter 3 of the IECC. For example, Tampa falls into the red section, or Climate Zone 2. Cleveland would fall into the green part of the map, or Climate Zone 5. In our example, Richmond falls into the yellow area, or Climate Zone 4. This is part of the table showing requirements for Climate Zone 4 of the IECC. The table shows R-13 plus 7.5 for metal-framed above-grade walls. The R-13 refers to the insulation required inside the wall between studs. Insulation after the plus sign is typically a foam-based continuous insulation board required on the exterior side of the wall. The continuous insulation is permitted to be installed on the interior side of the wall, but this is not often a practical solution. This provides a little more context for R-value terminology. The R-13 in the first part of the code requirement in our example refers to the insulation between studs, as shown on the right. The R-7.5 CI is the layer shown in blue between the sheeting and the cladding on the left. Notice the relatively long screws for attaching the cladding through the continuous insulation. The continuous insulation can be 3 or more inches thick depending on the climate zone. In most climate zones, CFS walls will require R-7.5 continuous insulation. So what does this mean in terms of insulation thickness? It depends on the specific product density and the manufacturer. Unfortunately, thinner products are generally more expensive. Polystyrene foam boards, usually EPS or XPS, will be between 1.5 to 2 inches. This makes for some very long fasteners for the foam and siding attachment. Polyisocyanurate would require the thinnest section at about 1.25 inches, but it is also the most expensive of the products. Price and thickness tend to be indirectly proportional. The next prescriptive compliance path again deals mainly with the thermal envelope, but is based on U-factors of the individual components. The U-factor represents the performance of the entire assembly, not just the insulation. For example, the framing in the walls or in the roof trusses would have a lower R-value than the insulation itself, lowering the overall assembly thermal resistance. The U-factor approach accounts for all members of the assembly. Let's apply the same 5-story example building in Richmond to the U-factor path, but this time using ASHRAE 90.1. This is part of the table showing U-factor requirements for Climate Zone 4 in the 2016 edition of 90.1. Going down the first column on the left to steel framed and then over 3 columns gives us a U-factor of 0.064. The U-factor is a maximum allowable value, so our steel-framed assembly must have a U-factor no greater than 0.064. Remember that this is different from the R value that only reflects the performance of the insulation versus the entire assembly. One point of clarification here is that you might see or hear someone talking about the effective R value of a wall. If that's the case, they're likely referring to the inverse of the U-factor for the entire assembly. Even though we've talked about U-factors, in reality you typically need to break that down to requirements for specific components that go into the wall. You can look for your assembly in published U-factor tables, such as in Appendix A of ASHRAE 90.1, to see if the components in your assembly match up. There are multiple assemblies that could work. For example, R11 plus 8 would comply with a 3 5/8 inch stud at 16 inches on center. It is acceptable to use a more commonly available insulation product, such as R-13 in this case, as long as it is an increase and not a decreased R value. If your wall studs were 6 inches instead of 3 5/8, then R19 plus 5 is an acceptable solution in the 90.1 appendix table. For windows, doors, and skylights, manufacturers provide the U-factors and products are required to be labeled. For fairly conventional steel-framed wall, floor, and ceiling assemblies, there are several published sources from reputable organizations. We've already mentioned Appendix A in ASHRAE 90.1, but keep in mind that 90.1 doesn't cover every assembly and it may be less accurate than test data. However, if using 90.1, then the Appendix A values are required unless your assembly doesn't appear there. For proprietary or innovative systems, the manufacturer would normally have to provide test data following ASTM 1365, or U-factors based on calculations. The IECC includes a calculation method in section C402. Note that the industry has conducted hot box tests over the years and has published them through the Cold-Formed Steel Engineers Institute. This document also covers calculation methods. It is always wise to check with your local code official before using a specific U-factor if it doesn't come directly from the code text. Although we've limited our examples to use of the prescriptive options for walls, the approach for roof, ceiling, and floor assemblies is identical. Look up the climate zone, find the R value or U factor in the appropriate table, and select or verify that your assembly or components are equivalent to or exceed those requirements. One difference is that the process for windows requires a unit to meet both a maximum U factor and a maximum solar heat gain coefficient, often just called the SHGC. It's not typically important to the framing system when using the U-factor or R-value prescriptive paths, but SHGC comes into play when looking at trade-offs in the envelope, or with the whole building performance compliance paths. This is probably a good time to talk about some of the challenges that continuous insulation poses for steel framing and buildings in general. The biggest challenge might be with fasteners. Although the fasteners are hidden in this picture, you can see the foam sheathing they have to penetrate to reach a solid surface for secure attachment. The fasteners have to be long enough to account for the thickness of the insulation, which again may be from 1 1/4 to 3 or more inches. Based on research supported by SFIA and others, the International Building Code adopted a set of prescriptive fastener tables in 2015 for attachment of cladding over foam insulation. But the code doesn't cover all types of cladding or stud configurations, so some assemblies will require an engineered design. If you look at the bottom of the wall in this picture, you see another area where some detailing is needed to cover the exposed foam. Metal flashing is one of the typical solutions. Corners, both inside and outside as shown here, also pose a challenge for thicker layers of continuous insulation. If the foam is too thick, there isn't anything to drive a fastener into but the foam itself. In this case, the builder uses a plywood strip that is attached back at the stud and extended out to the edge of the foam insulation. Jamb extensions will be required at windows and other openings. Hose bibs, lights, and other smaller items that hang on the wall need special fasteners too. One more point about the prescriptive paths in the IECC before we move on to other compliance options. At some point, more insulation isn't cost-effective. So to further improve a building's performance, the IECC adopted a series of mandatory additional requirements outside of the thermal envelope. You see the section from the 2018 code here. The impact on steel framing is not significant with these if you're willing to use the prescriptive paths. However, if the level of continuous insulation is not acceptable, and you look to one of the other compliance paths to reduce or eliminate the foam, then these do have an impact. The 8 items shown here are some of the improvements previously available to trade off continuous insulation. With them now being mandatory, it reduces the flexibility offered with the performance paths in the IECC. ASHRAE 90.1 still retains a higher level of flexibility by comparison. Next up, we'll look at the other compliance options in the IECC and 90.1. These are a bit more complex, and most require a computer software package, so we'll give just a brief overview of each. The prescriptive alternative paths are sometimes called a UA trade-off, meaning each area of the thermal envelope surface is multiplied by its code-required U-factor and summed to get a building total UA. You can then modify the U-factors for individual areas, as long as the total UA of your design doesn't exceed the code UA. For example, this could allow you to put in better windows in exchange for a thinner layer of continuous insulation. Or you could reduce the roof insulation by increasing performance elsewhere in the envelope. We've mentioned the thermal envelope a few times now. It's a simple concept, as shown here in this sketch of a 3-story building with a covered parking area off to the right. The thermal envelope is the area that separates conditioned space or semi-conditioned space from unconditioned space. This is shown in the red. Note the garage area is not conditioned, but if it were, the thermal envelope would look like this. A last point on this slide is that you would typically use a software package with these options, although you can do hand calculations for the IECC method. We'll talk about some software options in just a few minutes. The performance options in the IECC and 90.1 can be complex and require someone reasonably proficient with a software simulation model. All of the loads in the whole building are simulated and compared to a standard building as described by the code or standard. We'll focus on a few key points so you leave here knowing about some opportunities to design a more efficient building. Because this approach involves a variety of systems like those here, it is usually in the domain of the mechanical designer or architect. However, for the steel framing manufacturer, it wouldn't hurt to give them a nudge to at least look at alternatives to the prescriptive insulation values when they're too expensive to build. On the downside of this discussion, the codes, especially the IECC, have tightened up so much in all of the systems that they have severely reduced the opportunities for many meaningful trade-offs. However, there is still some flexibility by looking at increases in the efficiency of various systems as trade-offs against the insulation in the steel framing components of the thermal envelope. In most cases, you'll need to look at the combined impact of efficiency increases in multiple other systems to have a significant impact on insulation in walls or other framing components. The most common trade-offs required to offset some or all continuous insulation are shown here. For example, better windows would be a good trade-off in the southern climates. Similarly, shading of the building can be used to trade off insulation in the walls, ceilings, or other components. Other options include window area decreases, internal shading of glazing, mechanical ventilation energy, reduced duct leakage, or better lighting designs. Some credit can also be given for on-site energy generation. It would be nice to show some examples of building simulations using the various prescriptive alternatives and the performance options. Unfortunately, that would require a lot more time than we have today, but I do want you to know at least where to look for more information on these methods. You can see here the specific sections for the various methods in ASHRAE 90.1. The first one is the trade-off within the envelope, and the next two are two different whole building simulation options. The energy cost budget method has been in Chapter 11 of 90.1 for decades and is the most often used simulation approach. The performance rating approach is regulated to an appendix for now. It is a recent introduction and not very widely used or incorporated into all of the most popular software packages. These are the section references for the trade-off and performance options in the IECC. I mentioned before that the IECC has made some changes that reduce the benefits of running a whole building simulation or otherwise using a trade-off approach. The most significant change is this section, which requires a proposed design to use no more than 85% of a standard code building. This is designed to sort of make the performance and prescriptive options equivalent, by accounting for the additional prescriptive requirements in the IECC that we mentioned earlier and are shown here. These extra IECC requirements tend to make ASHRAE's performance options more flexible. For a lot of people, the first question they ask is, which software program should I use? Unfortunately, there's an overwhelming number of programs that have been developed, and each has its pros and cons, but at least three are worth mentioning. First is a package called Energy Plus, which was developed with P&L, one of the U.S. National Energy Labs. Energy Plus was developed to be the main system that does all of the detailed calculations necessary to run a building simulation, but it is just the engine. Although it's a free download, in order to be useful, it has to be paired with a user interface, of which there are many to choose from. The product website, energyplus.net, provides background on the software and information on available interfaces. However, the main reason you might want to consider an interface that uses Energy Plus is that it is considered the best and most widely accepted program for compliance with the IECC and 90.1. That doesn't mean others are not acceptable. In fact, some states, such as Florida, have their own approved programs that are excellent choices. Just be sure to check with the code officials in areas where you are working before heavily investing in any specific software. The cost of the software is not all that much compared to the time it takes to become a proficient user. If you are interested in this route, there are some programs that are much easier to use you could consider. They aren't as capable as a full-blown simulation program, but are acceptable for basic code compliance and some simple trade-offs. ComCheck is one such program for evaluating code compliance for commercial buildings. It was developed by the U.S. Department of Energy to address compliance specifically with the IECC 90.1 and a few unique state codes. The ComCheck website, which is at energycodes.gov/ComCheck, provides the following description of the product. ComCheck simplifies compliance for building officials, plan checkers, and inspectors by allowing them to quickly determine if a building project meets the code. ComCheck Desktop may be downloaded and installed directly to your desktop, while ComCheck Web is accessible directly from the website without having to download and install. Because it basically has the blessing of the DOE, ASHRAE, and the International Code Council, it is unlikely you would find a jurisdiction that would not accept ComCheck results in areas that use the IECC or 90.1. And hey, it's free. Just a quick note if you're building low-rise residential structures, such as townhouses or single-family homes. There is a companion to ComCheck for these buildings called ResCheck. It's also available as a free download at energycodes.gov/ResCheck. This brings us to the close of our presentation. Here are a few takeaways from the program. Energy codes are now more important than at any time in the past. CFS assemblies are no longer standalone products, but need to be integrated with a thermal envelope design. The prescriptive R-value compliance path is easiest to use, but does not always result in the most cost-efficient design. Almost every building will need continuous insulation on the exterior walls under the prescriptive options, and this can be expensive and technically challenging compared to past practices. Trade-offs under the prescriptive alternative options in the whole building performance paths offer more flexibility and opportunity for the most economical designs, more so with ASHRAE 90.1 than the IECC. Thanks for your time and listening today. For additional information on energy performance in CFS buildings and other SFIA programs, please visit cfsteel.org.